Today we're going to talk about radioactivity. These are some things that might come to mind when you think about radioactivity, right? You may think about radioactive waste or nuclear bombs or nuclear power plants, or maybe you think about radiation sickness like we saw in the video, or maybe you think about medical procedures and radiation therapy. These are all to do with radioactivity. Some isotopes are radioactive. So far we've been talking about isotopes, and I've just been kind of throwing around the word isotopes. Well, it turns out that some atoms, some isotopes are radioactive. Some isotopes of elements are unstable, and when they're unstable, we call them radioactive. They have too many protons or too many neutrons, and that's what makes them unstable. Large elements, number 84 and up on the periodic table, are in fact radioactive no matter what. Small ones can be radioactive too. So let's talk about what is radioactive. What determines if a nucleus is radioactive? The neutron to proton ratio is an important part of stability. Small, stable atoms want to have one neutron for every one proton. In other words, they want to have a one neutron to one proton ratio. Bigger, stable atoms are happy with a 1.5 neutron to one proton ratio. We call this the band or the belt of stability, and I'll show you what that means. The belt of stability runs right here in the periodic table. Now, let me explain to you what we're looking at here. If we were to look at the periodic table and we were to put all of the elements along the bottom of this x-axis, and you were to have element number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to element 20, which is calcium, element 40, which is, I'm grabbing my periodic table to look because I don't even know what it is offhand. It's zirconium. Element 60 is going to be way down at the bottom, neodymium. Anyways, that's what these are. These are the atomic number, or in other words, the number of protons, right? On this side is the number of neutrons, right? If we add those numbers together, we get the atomic mass. So you can see here, as the atomic number increases, the number of neutrons increase. This line right here is your one-to-one line. This would say at element number 80, if you had 80 protons, you would have 80 neutrons if you were right here. Well, it turns out that 80 protons and 80 neutrons are not stable. They fall below this band or belt of stability. Alternatively, anything past 84 is not stable. It's past the band or the belt of stability. This line is kind of our magical stable line right here, this band or belt, and I can't decide which word I like more, of stability. So you can see here, for about atoms 1 through 20, which would be hydrogen through calcium right here, it's about a 1-to-1 ratio, and then it starts to take a turn, and it starts to move more towards that 1.5 to 1 ratio. So as the atomic number increases, that's here, it starts to increase above 20, the neutron-proton ratio starts to get closer to 1.5 to 1. That is the definition of the belt of stability. So let's take a look at another graph. It's the exact same graph, it's just another way to look at it. At the bottom of the graph is always the number of protons. The number of protons is going to be the same as the atomic number. On the y-axis of the graph is the number of neutrons. You can see here that elements 1 through 20 are about at a 1-to-1 ratio. That means that's where they're stable. Then as we move above, they start to become stable and move away from the one-to-one line. So this right here, this is our band or belt of stability, is right here. That means that if I have element number 60 from the periodic table, which is neodymium, it is stable if it has about 90-ish neutrons, right? So let me show you another example. Let's look at element number 70. Element number 70 is ytterbium. There would be, if element number 70 had 70 neutrons, it would be way below the belt. So we're going to go all the way up to the belt of stability to see that element 70 is stable right around there. Let's call it, 105 or something like that. That's how you read this graph. You can also read it and not even look at the graph and just kind of do it mathematically and say, well, we know that element 60 is not going to be stable with 60 neutrons because I know it's going to fall below this belt. Whereas element number 10 down here is stable with 10 protons and 10 neutrons. Now take a minute and look at the periodic table. And you're going to find that you will see this same exact pattern. So if you look at the periodic table, you'll see that oxygen, for example, number 8 on the periodic table, usually has a mass of about 16. That's to say that usually there's 8 protons, and usually there is 8 neutrons. Not that oxygen 17 doesn't exist. Nitrogen, usually there's 7 protons and 7 neutrons. But as we move along, all the way down the table, we can see, for example, manganese, element 25, is starting to make that turn. It's a little bit more stable above 50. If you go to element 50 or tin, notice this doesn't say 100. This is not 50 protons, 50 neutrons. We're edging up now towards 120. And that's because of this belt or band of stability, and it moves away from the one-to-one curve. So again, the belt of stability is the portion of the graph that contains all the stable nuclei. Nuclei with 84 or more are automatically radioactive. Nuclei above the belt go through beta decay, and I'll explain what that is in a minute. And nuclei below the belt go through positron emission or positron decay or electron capture. And again, I'll explain what that means. Past 84, it goes through what's called alpha decay. So above the band is beta, below is electron capture. Past the 84 line here is alpha decay. Okay, so this word radioactive. Radioactive happens when an atom has an unstable nucleus which breaks down and gives off particles or energy. That's what radioactive means. It doesn't mean radioactive man or the Incredible Hulk or anything like that. Radiation is the word that we use to describe the particles or the energy that's given off. Nuclear radiation would therefore be these particles or energy that are given off when we're talking about nuclear chemistry. The unit that we use to measure radiation exposure is called the sievert. There's also rem, or roentgen equivalent for man. That's another way that we can measure nuclear radiation, but you'll hear about these two terms and how dangerous radiation is. There are 4 different types of radiation. So this is where it becomes a little bit mathematical. The first type of radiation is alpha particles. The second is beta. The third are positrons. And the fourth is gamma radiation. Now I want to go through each one of these individually. An alpha particle is the biggest type of radiation. Okay, an alpha particle contains two protons and two neutrons. That's what an alpha particle is. In fact, an alpha particle is exactly the same as a helium atom. And a helium atom, of course, usually, when it's an alpha particle especially, has a mass of 4 and has two protons. Therefore, this is what an alpha particle is. Alpha decay, during alpha decay, it means that an alpha particle is lost. So if americium-241 goes through alpha decay, it means it's lost an alpha particle and turns into neptunium-237. The atom's atomic number goes down by 2 because it's lost 2 protons, and the mass number goes down by 4. The second type of radiation is beta decay. Now, beta decay and positron emission are going to be very similar to each other. In this type of decay, a neutron changes into a proton. What? A neutron can change into a proton? Really? I didn't think that could happen. Well, guess what? Welcome to nuclear chemistry. It can. So in this example, I have this blue neutron here is changed into a red proton. Now, when that happens, the atom's atomic number is going to go up by 1 because we've gained a proton over here. And the mass number is going to stay exactly the same. This one has a mass number of 3. This one has a mass number of 3. So hydrogen 3 is going to become helium 3. What gets released here is a little tiny particle we call a beta particle. And a beta particle is about the size of an electron and has about as much energy as an electron. The next type of decay is called positron emission. This is the opposite of beta. This is when a positively charged electron is released. What? A positively charged electron. A positively charged electron, instead of being an electron with a negative charge, is now an electron with a positive charge, is released when the proton changes into a neutron. So in this case, I have an extra proton over on this side, and then I change it into a neutron. The atomic number, and I'm sorry that this is hidden, the atomic number, this says decreases by 1. Again, just like the last time, the mass number does not change. Okay, carbon 11 becomes boron 11. And the last type of radiation I think is the most simple to talk about. It's gamma radiation. Gamma radiation is when just high energy light or a photon is released. Okay, gamma rays are just light waves. They do not change the mass or the atomic number. It turns out these are the most dangerous of all types of radiation, even though they're the smallest. And the reason that they're the most dangerous is because even a cement block, a metal block, a wooden block, none of these can stop gamma rays. If you look at this, it shows the penetrating power of these particles. Alpha particles are big, heavy, slow. Paper can stop an alpha particle. Beta particles can go through a sheet of paper, but your hand can pretty much stop a beta particle. And then, like I said, even a metal block cannot stop penetrating gamma radiation. So let's look at the way we draw the notation for these. Alpha particles, like I said, are just a helium atom. So they can be drawn like this to show that they're a helium atom. This is the nuclear symbol for helium. Or you can draw, this is the alpha symbol. These are exactly the same thing and will be interchangeable. A beta particle is a little bit trickier. A beta particle is showing you that an electron is released, so you can use these two notations. And a positron is the opposite of this. You have this for your you're going to use for your nuclear symbols, and here's the beta symbol. This does say or E plus, so it's worth mentioning that this could be E minus or E minus 1. And then the gamma radiation, this is what the symbol looks like. We're not going to use it very much for the formulas since it does not change the atomic number or the mass number at all. So let's do some of these problems. Here's an example of alpha particle radiation. So if you start out with this isotope, it's called uranium-238. When it decays, and that's what that is, that's an arrow to show the decay, it turns into thorium-234, all right? And it releases this particle, which is the alpha particle. So again, uranium-238 releases an alpha particle to become thorium-234. If you follow this formula, you can think of this as an equal sign, right? Uranium-92 equals 90 plus 2 equals 92. 234 plus 4 equals 238. That's how we do these equations. Here's beta emission. This is, again, an arrow here that you can think of in these equations as kind of an equal sign. You've got carbon 14 is going to go through beta decay. Remember, beta decay is when a proton or a neutron is changed into a proton. So the atomic number goes up by 1, and the mass number does not change. And you can see that reflected in this equation, 7 plus a minus 1, or in other words, 7 minus 1 equals 6, 14 plus 0 equals 14. And positron is the opposite. You've got oxygen that is going to decay, oxygen 15 in this case, is going to decay into nitrogen 15. So this proton is being turned into a neutron. So our atomic number is going to go down by 1, and the mass number does not change. Check the equation. 15 plus 0 equals 15. 7 plus 1 equals 8. Here's a few more examples. I suggest you pause the video and give these a try on your own to see how you would do. Okay, this one. Carbon, this is carbon 13 in this case. Carbon 13, the way I like to do these formulas is I like to look at the 4 here, and I like to imagine that I know that 11, or I'm sorry, obviously not 11, thank you, Mrs. Robles. 9 plus 4 equals 13. I also know that 4 plus 2 equals 6. And then I go to my periodic table. I find out what number 4 is on the periodic table, and it turns out that that is beryllium. So that's how I fill that in. I'm going to do the same thing here. I'm going to say that 94 minus 1 equals 93. And then this number does not change. This is 239. Plus 0 equals 239. So I go to my periodic table. I find number 94 on the periodic table. Turns out that it's plutonium, or Pu, and that is what I make. In the last example of positron emission, I've got phosphorus 32. So again, I know that 14 plus 1 equals 15, and this is going to be 32. So I go to my periodic table, and I find out that this is silicon. So I'm left with beryllium 9, plutonium 239, and silicon 32 when these types of emission are taking place.